Hello and welcome everyone. So while we wait for people to join the Zoom link, I would like to do a quick sound check before we start. So if you can hear me, please type yes in the Zoom chat tab. I will also share a link in the chat where you will get instructions to download the code that Matt will be covering along with the doc that has all the necessary R packages that will be covered during the meetup.
Hey everybody, thanks for tuning in. I'm Matt, by the way. Where are you guys all coming in from? Ooh, I see Alan from Tucson. We got Les from LA. Ooh, Germany, Switzerland, Edinburgh. I see. I see Tanash is from Edinburgh. That's one of my favorite spots. It's where my wife and I when we first started doing a lot of traveling, obviously before COVID. Edinburgh was fantastic. Definitely, if you haven't been there, you should check it out.
Hi, Erin.
We got Toronto, Denver, Ecuador. Wow.
Love it.
Yeah, and then we have Erin from Oakland, California. How's it going, Erin? I think I'm going to bring Erin up in the presentation here in a minute.
Okay, so thank you for joining us today to learn more about Modeltime H2O, which is part of a growing forecasting ecosystem in R. My name is Bruna Smith. I'm on the marketing team here at H2O.ai. And for those of you who don't know H2O.ai yet, we're a visionary software company founded 9 years ago in Silicon Valley that brought to the market new platforms and technologies to drive the AI movement. Our speaker, Matt Dancho, is an avid member of the data science community and has contributed software in time series and finance. He is the founder and CEO of Business Science, an educational platform and school dedicated to applying data science to business problems. Before I hand it over to Matt, I'd like to share that we'll have some minutes for Q&A towards the end of the meetup. So please feel free to send us your questions via the Q&A tab on Zoom. So without further ado, I'd now like to hand it over to Matt. Welcome.
All right. Well, thank you so much. I appreciate it. Thanks for having me. I've been using H2O for quite a while. And I'll talk more about that here in a second. First, I'm going to put in the link. So if everyone check the chat window, this is going to be a link to get access to all the code that I showed today. So I want to give you that first. So that way you guys can start logging in, getting the code, getting the cheat sheet and that sort of thing. And yeah, with that said, I'm going to share my screen. If you can do me a favor, when I share it, is it showing up? Can you guys give me just a quick thumbs up? Okay, cool. All right, you can see it?
Yeah.
And all right, I'm going to hit the presenter view so I can see it. And we should be good to go. Okay, cool. So this is a training on a new software package that I've developed, and it's part of a growing ecosystem. So Bruna had already mentioned that. We'll be focusing on Modeltime H2O, which is for forecasting with the H2O AutoML machine learning portion of the H2O library. So it's really cool. It's quite amazing. And we'll see some of the benefits, like how little code that you have to actually write in order to be able to do some pretty sophisticated forecasts. So with that said, we're going to be focusing on this package specifically, but we'll also be talking here a little bit more about the broader ecosystem, which is called Modeltime, and it's a growing forecasting ecosystem. So just quick agenda. I have the H2O code demo, so we're going to hop into that first here. It's going to take probably about 20 to 30 minutes or so. And then I have another section where I'm going to be talking about the broader ecosystem for high performance time series forecasting. And then I'll reserve probably about 10 minutes or so at the end for some Q&A. So just to add to what Bruna had mentioned at the beginning, my name is Matt. I am the founder of a company called Business Science. We are an educational provider. I have several courses, and I'll actually talk a little bit about my relationship with H2O. So I mentioned Erin Liddell. I told her I'd pick on her a little bit. Erin heads up the AutoML team at H2O, and basically this is it's just an amazing software. It's one of the when I first got into R, actually a little bit before that, so probably 4 or 5 years ago, H2O had come out with this algorithm called AutoML, and that's how I really got to know the H2O company. So I started using this, and back then, business science wasn't around. I was working as a director at a company that manufactured valves, and I was using it to be able to kind of like glean insights. And they came out with this AutoML product. I fell in love with it. It was something that honestly like made my life so much easier because before that, machine learning was really, really challenging. You had to write a lot of code, and from a productivity standpoint, it just wasn't very good. So fast forward, I've been using H2O for quite a long time. I love them as a company. I'm a huge fan. And Erin and I have actually grown even closer because the first course that I developed as part of business science actually teaches H2O. So we're unfortunately not going to be really talking about that today, but it's kind of funny. H2O AutoML was one of the first things that I started teaching because it was what I was using so much as I was doing consulting and as I was working for previous companies. So yeah, that's my brief relationship at 1,000-foot view of H2O, and I really honestly I am a big fan. Erin's actually in our Slack channel for our educational platform, and she's in there with me answering questions on H2O all the time. So it's been a really good relationship. All right. So with that said, we're going to jump into some code now. We can talk a lot about, H2O. We can talk a lot about model time, but the best way to really understand it is to actually show you. So if you guys go to the link that I had sent out, it should give you access to all of the code. So you just kind of, it'll send you an email. It'll give you a link to the code. It'll give you a link to the cheat sheet that I'll be talking about here in a little bit. So we have some files over here, and this is the project. So if you've used RStudio before, you just click this .r project file, and it'll open up the RStudio IDE in the correct directory. What we're primarily going to be working out of is this file here, forecasting_modeltime H2O.r. So you want to click that. This file will open up. If you don't see this outline over here, just click this little button, and that'll pop up. So I'm going to just start running through some of the code. This is a quick H2O workshop. The objective is that we're going to forecast for the next 52 weeks of data. This is a data set that is actual sales demand data, and it's multiple time series that we're going to be forecasting, which is one of the real advantages of being able to use model time and H2O together. And I'll talk more about that in a second. Libraries that we're going to load, if you are unfamiliar with the R ecosystem, it's grown dramatically. There's this new modeling system called Tidy Models. It's very similar in respect, if you're a Python programmer, it's kind of like scikit-learn. What they've done is they've standardized a bunch of machine learning packages. So I'm just going to run through and hit Control and Enter. We're going to load Tidy Models. We're going to load modeltime.h2o. We're going to see that behind the scenes, it's also loaded model time in the H2O package. And we're going to load the tidyverse, which is kind of like the core packages in the R ecosystem, like dplyr, tidier, ggplot, and those sorts of packages. And then we have another software library called TimeTK, and this is one of my libraries as well. It's for time series analysis. And I'll try and point out kind of where some of these functions that we go through today, which packages they belong to, so you can kind of understand the ecosystem at a high level. The data set that we're going to be working with looks like this. It's called Walmart Sales Weekly. It comes from the Time TK package. And if you can see down here, it's what's called a tibble. It's 1,000 rows by 17 columns. So you'll notice here that there's a timestamp feature. There's a weekly sales number, and then there's a store, an ID, which is a combination of store and department. So those are the three columns that we're primarily going to be working with today. There's other columns that are just kind of like, we'll call them engineered features or different, it's multivariate, but we're going to make this mainly just an ID, date, and weekly sales. We're going to be working with those three features. So that's what we're going to store here. First, hit Control and Enter, and this is done is just kind of pared it down. So it's just the ID, date, and weekly sales. All right, so now that we have our data, what I'm going to do is just do a quick group by ID. And what I'm going to do is basically show you what these time series look like. So when I run this section of code here, and I'm going to open this up just a little bit so we can see what the data set looks like. So these are the 7 time series that are in our data right now. So you can see 1_1. This is that first store and department combination. 1_3, first store, the third department. 1_8, first store, the 8th department, and so on. And you can see that these departments have kind of different sales patterns. This blue line is what's called a smoother. So this is the plot time series is doing the heavy lifting. That comes from the Time TK package. And it just kind of creates all of these interactive graphs for us. Pretty nice. Next thing I'm going to do is just assess the seasonality. So from a time series perspective, a lot of times it's good just to be able to take one of these time series and see if there's any like seasonal patterns. And that's what I'm doing here. So I'm going to hit Control and Enter again. What this does is it gives me the unique IDs. I'm just going to filter to one of the IDs. So this ID, it's going to be the second one, this 1_3. And I'm going to hit Control and Enter. And this is going to give me another plot here where we can see, there's a week, looks like there's a weekly sales cycle, a week of the year. Looks like the 35th week of the year seems to be pretty important. Looks like sales kind of spike over that week. That tends to happen in August, which we're seeing right here in the third quarter, and so on. We can kind of go back and forth, do maybe another, this is a different time series. This is the first time series, which is 1_1. And you can see a completely different sales pattern. So you've got December tends to be the high point of the season for this particular department. Also April and February. Maybe the Super Bowl time of the year and April, springtime tends to be kind of high sales patterns. Okay. So we now know a little bit more about these time series. Let's take this time series and turn it into a forecasting problem. So what we're going to do is we're going to set up a forecasting horizon. What we're going to, the objective or business objective is the next 52 weeks. We want to understand for each one of these time series what the projected sales are going to be. So we're creating a forecast horizon. I'm going to split it using this time series split. Comes from the Time TK package. We're going to assess 52 weeks, and cumulative equals true tells it to take all the other data and put that into a training data set. So basically what this does, this time series split, if I run these next few lines of code, kind of shows you how we're splitting up the training and testing. Now, normally you can see here, there's 1 sales cycle, 2 sales cycles, so just about 2 sales cycles. I normally like to have a little bit more data in the training set. So 52 weeks is kind of a longer forecast than what I normally like to do. I like to have normally like around 80% of the data in our training, but we'll go with it for this analysis. Okay, next thing that we're going to do, we're going to take and come up with some pre-processing steps. And what this does is it helps our H2O algorithm grab onto different key features within that data set. So if you remember, we took a look at the seasonality, and it looks like there were different seasonal features like month of the year, week of the year, and so on. We're going to add those into our data set now. So we're going to start by creating a recipe from our training data. So we're taking the training, we're using this function called training, calling it on splits, and it pulls in 637 rows of data that are in our training data set, which is this blue region over here. And then we're going to add on a step time series signature and on our date feature. And I'll show you what this does in a second. And then I'm also going to normalize some columns that are produced from this step here. So I'm going to run this. If I do control enter and then one more control and enter. So our training data set goes from just being the ID, date, and weekly sales columns to now having a bunch of other features in here. So we've got things like the date index, the date year, the month labeled, and so on. So we've got, these are what are called engineered timestamps or calendar features. It's just added those in there. I'll talk more about calendar features here in a minute, but they're really important for doing machine learning, and they prove to be very important for certain forecasting techniques. Okay, now we're ready to do some modeling. So we're 63 lines in, and we're already ready to do some modeling. So what I'm going to do is I'm going to fire up H2O. So you do that with this H2O init function. I'm just running H2O locally, and it started up an H2O cluster. Optionally, you can turn the H2O no progress. You can turn off the progress bars. I'm going to leave them on just so we can see the progress going as we're running our models. The next thing here that we're doing is creating a model specification. So this is part of the tidy models kind of structure. So when you learn tidy models, you'll become very familiar with these styles of functions like AutoML_reg. So this is creating an AutoML specification. When I hit control and enter, we can see down here that creates an H2O AutoML specification with the computational engine of H2O. We're going to set the engine, and then these are various parameters that get passed on to the underlying algorithm, which in this case, we're using H2O AutoML. So when I do that, I'm going to create this model spec H2O. It's not fitting anything. It's just saving the parameters that we want to use. So we're going to set it to max runtime seconds and so on. This next step here is where the fitting takes place. I'm going to run this just because it does take a few seconds. And then I'll kind of explain what's happening. So we see that H2O is training. How I accomplished that was I created what's called a workflow. And this comes from the Tidy Models ecosystem. So Modeltime is actually an extension of Tidy Models, where we're adding a model and we're adding a recipe. So the model that we're adding is this model spec H2O. The recipe that we're adding is this recipe spec. And what it's saying is it's going to combine those two, and then it's going to then fit those on the training set. Okay, it looks like it's done. And we can see that the output here is looks like a stacked ensemble. So we now have completed our training, and we can see we've got this workflow. It's called a workflow fit H2O. It's also in my environment over here. So you can see it's a large workflow, 4 elements, and I'll actually open it up over here so you can actually explore it. It's a workflow. It's got all sorts of crazy stuff in here. It's a big object. And we'll talk about some of the different aspects here in a minute of what that object contains. So the main thing is that it's basically a model that we've created that's been fitted. And we can do cool things like that. What you can normally do with H2O is you can see what the leaderboard is. So that might be something that you want to check out. So Modeltime H2O comes with this AutoML leaderboard function. Hit control and enter, and you can see that the AutoML leaderboard has been saved in here. So when we were fitting, we were actually running H2O AutoML on the time series, and it was creating a bunch of models. So we've got 32 rows, so 32 different models. And you can see that it's a leaderboard. So they've all been ranked. And by default, what's been selected is the top model, this stacked ensemble. So when we see this, this model here, It's a H2O regression stack model, model ID. That's what's inside of this workflow fit. So it saves that top model. But we can do cool things beyond this. So one of the downsides, so the upside with a stacked ensemble is it's going to be your best predictor. The downside is it's not necessarily explainable. So you could also maybe take the third model here, which is XGBoost, and you get some additional benefits from that one. It may not be quite as accurate, but you can actually explain it. So if we grab this model ID here, what's nice is I can actually take that workflow fit object and I can switch out to any of these models that I want. So I'm going to remove this one. This one was from an old training run. So I'm going to save this as XGBoost. I'm going to update it. So now, and this doesn't actually update the physical. I would have to overwrite this, but I just want to show you how you can quickly swap out these models. I thought this was pretty cool. So now if I wanted to, I could create a new workflow called like workflow 2. And it would be using this XGBoost model, which is the third model in our leaderboard. And then what's cool here too is that I can actually save it as well. So I'm going to go into my files here in this H2O models folder that I've previously created. I already saved one. I'm just going to delete this one out just to prove to you that I'm saving another one. So what I'll do is I will just run these 2 lines of code. And this is my XGBoost grid 1 here. So if I open this up, it's got the Modeltime RDS and the H2O underlying H2O model saved into this folder here for me. And then if I wanted to, I can then load that model by just pointing to the directory that contains that. So if I wanted to load it, it loads this back in, and you can see it is indeed the XGBoost grid 1 that we just saved. Okay, so that is kind of the basics of like exploring the H2O. Now let's move on to actually forecasting. We haven't done any forecasting yet, and I want to do some forecasting. So this is where we get into the model time workflow. It's I call it like a best practices. It's basically what I do in order to ensure that I'm getting good forecasts, both from a prediction level and a confidence level. So I want it to be accurate, but I also want to be able to measure, kind of understand how confident I should be in these forecasts. So we're going to kick off a full model time workflow. It starts with creating a model time table. So I'm going to, in here, I'm going to change it, make sure I change this out to the new model. And when I just run these 2 lines here, you can see here that it has updated, it basically has created this thing called a model time table. It contains the models and then also a description of each of the models. So you can see the first one's a stacked ensemble, the second one's an XGBoost. So what is nice here is that this model time table stores everything for us. It's more of like an organizational tool than anything. So I'm going to store those in my model time table. The next thing I'm going to do is I'm going to do this thing called calibration. And you may never have heard of calibration before, probably why, because I came up with that term. But it's something that, I call it calibrating, but basically what we're going to do is we're going to run each of our algorithms on the testing sets. And what I want to do is I want to store what the residuals are from our analysis. The residual analysis is really important. So I'm going to run that now. And you can see that it's actually doing some predictions for me. And now what it's stored is a new column called calibration data. So basically it took my test set and it stored what the actual values were, what the predictions were, and then what the difference were between the actuals and the predictions, which is called the residuals. And that's going to help us determine our confidence level, how confident we are in these forecasts. So what we can do is we can do calibration tibble, pipe this into model time _ accuracy, control enter, and we can actually get accuracy levels on each of these different forecasts. And again, this one's the top one, the stacked ensemble. And you can see we're getting around 0.978 R squared, which is really, really good. And then it's also got the lowest RMSE, lower is better. So it's doing pretty well. The next thing we're going to do is we're going to actually visualize the forecast on the test set. So this is going to, again, run some predictions for us, and it's going to pop out a chart here. So the first part of it creates the data, and then the second part of this, we're grouping by ID and then plotting. We're using a plotting utility so we can see what these forecasts look like. And they're looking pretty good. So we can see here that it's catching a good bit of what we'll call the variation. So it's catching this spike pretty well. It's missing this spike a little bit, but overall it's doing a pretty decent job. This one over here, it looks like it's catching almost perfectly, and so on. So you can examine each of the different time series. So to take a step back, what we just did is pretty miraculous. If you think about it, we created one H2O model, or actually two H2O models that we're modeling, and we've just predicted that on 7 different time series all at once. So this is what we call a scalable or a high performance system that's meant for scale, because we didn't have to run through a loop for each one of these. We just created one model and it predicts all 7 of the different time series at once. And it makes for a very scalable system. We'll talk more about that here in a minute. The last bit here is just kind of a best practice. What we normally do before we predict the future, what we normally do is we retrain on the full data set. So we've only trained these models up until this point here, and then we've predicted forward. What we normally want to do is we'll capture what our variation is, but we'll actually create new models with the full data set, and then use the confidence level from our test data set to move forward. So I'm going to hit Control and Enter. This refit table now is refitting each of the models. It will take a minute to run because it has to rerun through the H2O AutoML process, and it's going to go back through. One point on this, I know Aaron at H2O is working on also allowing us to just use specific models during the retraining process, which will make this go a lot faster. So we don't have to necessarily retrain all of AutoML again, but rather just the top model or the model that we've selected, just retrain that model. That is a GitHub request that we received from a user, and I believe they're working on it. Okay, it's through the first round. There's actually 2 rounds of training that need to happen because we had 2 different models in there. If you remember up here, when I saved it with 2 different models. This one came with the top model, and then this one came with the XGBoost model. Okay, so once that's done, what I'll do is, and it looks like it just finished up, I'm going to take my refit tibble, which looks like this now. We see that there's an update here. So it has updated this model, the second model, and it's converted it from an XGBoost to a stacked ensemble. Surprise, surprise, the stacked ensemble won during that second round of refitting. So if we wanted the XGBoost, we'd have to physically go in and re-update that. I'm just going to show you what the future forecast looks like. I forgot to run this line of code. So we're going to use the future frame function to extend our testing data set into the future. And then we're going to take that refitted data and basically run the same code. This time, instead of visualizing the test region, we're actually going to forecast into the future. We can see that these 2 models are the exact same. And that's because we ran a seed, and during that second round of training, the stacked ensemble won both times. So these are actually reproducible algorithms. And you can see that these 2 ended up being the exact same. Okay, and we're done. So that's it. 173 lines of code. We've just forecasted 7 different time series, and we're feeling pretty good. All right, so that is the Modeltime H2O in a nutshell. There's a lot more to it. There's a lot more to the Modeltime ecosystem, and I want to talk about that a little bit now. So The key idea and what prompted me to really step down this path of coming up with this model time ecosystem is that I've noticed over the past several years, and it's getting worse and worse. Business forecasting is changing, so we're seeing data sets that are higher and higher frequencies, meaning it's not like a monthly aggregation, but rather businesses want like product level data on a daily frequency, or sometimes even sub daily if it's like, they want to know what their website traffic is by hour, and if they're having an anomaly, they want to have something, alert them. These are the types of questions that businesses are now starting to ask, and because of this, it's the requirement for scale is increasing quite vastly. So we need automation. We need to be able to handle higher frequencies, and need to be able to have scalable forecasting systems. So this is not a joke. I once did a consulting project where, basically the company that came to me and said, hey, I need your company to help us out. We need to improve our forecasting. And I said, oh yeah, okay. Well, what are you trying to do? He's like, well, we've got about 10,000 products, and we need to forecast them, every day. And we want to know if there's spikes in volume, if we need to adjust manufacturing. And I said, wait a second, you've got 10,000 forecasts that you need to be run every single day. So this was kind of like the light bulb in my head. I said, hey, this is going to take it. This is a different type of problem than I've ever, dealt with before. Normally it was just, I was working for my last company. I was forecasting with Arima, and I was doing it probably like once a month. And I would just forecast, hey, these are the next 3 months worth of sales, at like an aggregated level, at a maybe east, a regional level, like east, west, south, north regions, and so on. So we're seeing a big kind of shift in these requests for the companies. So when that company came to me and they asked for, the 10,000 forecast, I was obviously pretty shocked. But, when I started thinking about it, it's, well, what they're really asking for is a high performance forecasting system, something that can do this at a product level or at a customer level, or SKUs, that type of level 10,000 times, and they need that pretty frequently. So what that meant to me was that time series is now shifting, and we're seeing, and I saw this not only from the client's requests, but also I saw what other, some of the companies and the competitions that were happening out there. And what I saw was, forecasting back when I was doing it, it was just a monthly series. You might have like 10 or so time series, or maybe 100 time series that you had to forecast. And you're normally just running a loop, and you're just using like Arima. Well, this change in the way that companies are analyzing their processes and the problems is requiring the data scientists to get new skills now. So we've got forecasting in 2020. We're talking daily series. We're having scales of up to 10,000 plus time series. And then also new technologies that are needed to be able to answer these questions, which H2O AutoML is definitely one of them that falls into that category because it's a very scalable algorithm. So to kind of dive into this a little deeper, there were really 3 properties when I started analyzing this problem to begin with of what companies wanted. And the first property is a high performance time series forecasting system really needs to deliver the best possible results given your resource constraints. So this means that if you're trying to produce forecasting results on a daily basis for 10,000 products or 10,000 customers, then you need to be able to probably sacrifice something. We can't run Arima 10,000 loops unless we spread it across AWS and 10,000 clusters, so that probably isn't, economically that smart, but, it's certainly doable. But another path forward is trying to utilize some newer technologies, and we'll talk about that here in a second. But first off, it should improve your results. It should deliver really good results given your resource constraints. Then second property of a high performance system is you should be able to produce and adapt your data science as needed to report the accuracy. So the example that I always say is, a lot of times we fall, as data scientists, we fall in love with algorithms, and we say, hey, okay, I just learned ARIMA. So every forecasting problem then becomes an ARIMA problem. And I'm, constantly trying to use the same hammer when really I need a screwdriver, and I just didn't realize it. And that ends up being the case all the time with forecasting. I can't tell you how often I'm shocked by the results, because it's, I'm getting better results from maybe an XGBoost model when I thought, initially going into it, ARIMA was going to be the best. So you need to have an ability to adapt your algorithms as needed, and you need to be able to rank those algorithms and report the accuracy. You also need to be able to do this so you know that nothing screwy is going on. You're getting decent results. So this is an example of the accuracy table from Modeltime. So it's basically this thing up here, this Modeltime accuracy. If you pipe this into table, Modeltime accuracy, it'll give you a nice little table here. And normally you'll have probably a lot more algorithms in here than just two, but you can rank them. You can get the R squared and sort them accordingly. Okay, so the third piece of it is it should be scalable. So you should your organization has a ton of data, and the challenge is that you need to be able to forecast it to their needs. So if they say I need it at a daily frequency, you better be able to do that. If you go back to them and say, well, I can only do that once a quarter, when they need it daily, that's going to be a problem. So it needs to be scalable. So this, being able to scale out your analyses and be able to provide accurate analyses for every single time series is essential. So when I started researching this problem of high performance forecasting systems, it led me actually down the track of analyzing a lot of competitions. And the reason I was doing this, I actually, I'm not a huge fan of Kaggle competitions. I think a lot of people get a skewed vision of what data science is. But in this case, it's actually turned out to be really useful. So these data science competitions, what was unique about them on the forecasting domain is that they were starting to have these forecasting competitions on Kaggle, and these other competitions called the M series of competitions. So there's M4, M5. They dealt with this problem of scale, which is unique because most time series that's taught in academia is all, hey, I'm just dealing with one time series and I'm trying to figure out how to forecast it with ARIMA. So these were unique problems, but they were very similar to what the problems that I was seeing in business on the consulting side. So what we'll do is we'll just kind of step through a few of these, and we'll try to understand what takeaways we can glean from some of these competitions. So the first competition that I started studying was this Walmart sales competition in 2014. And this is a cool competition. The second place solution was actually the most practical. So what Srihari Jagannathan did was he ensembled different machine learning approaches using calendar date features. So what he found was 6 bad models make one good model, and the power of ensembling. And what he did was he basically did just an average of his 6 different models, and it actually improved his performance substantially by about 10% or so. The other thing that he did was he used a lot of calendar features, which is one of the things in machine learning you can do with time series that tends to help improve your models. So that was the first key takeaway. So when I started studying these, it was really impactful because it was completely different than what I was reading about, in some of the other time series analysis that were classically taught. The next thing, I checked out another competition. So the second competition is this website traffic forecasting. And what I started to understand was that, okay, there's even newer techniques out there that are being implemented. So this particular person, Arthur Solon, this is the first place solution. What he did was really unique. He ended up getting about 5 to 10% better than the second place solution, which in a forecasting competition is a wide margin. by implementing a deep learning strategy. So he used TensorFlow with an LSTM. Now, this his solution was probably one of the most complex that I've ever seen. I mean, literally, it probably took him 3 or 4 months just to write all the code for this thing. So from a practicality standpoint, it wasn't very practical. But from a technological perspective, we saw the rise of deep learning and how deep learning can be an effective strategy. So all we need is just somebody to help kind of package it so we don't have to write, 20,000 lines of code. So the takeaway there was deep learning. This is the third competition. This is the M4 forecasting competition. And again, we saw deep learning kind of be, be the top solution. So everyone else was using more classical algorithms like ARIMA and so on. But what the winner of this competition, Smil from Uber Technologies, won it with a large margin of victory by combining deep learning with exponential smoothing. So an exponential smoothing algorithm was so basically an ensemble using deep learning and a classical approach. So won by 3%, which is a big margin versus the second place. And then the fourth competition that I analyzed, and this is the most recent one, M5 competition. This is a unique one because they're actually forecasting at a daily level sales demand. It's very intermittent, which means there's a lot of zeros, meaning there's no demand, and then all of a sudden there's some demand. And they're having to model it both at the product level, at the department level, at the state level or the store level, and then at the overall sales level. So they have to model the whole hierarchy of sales, everything from the lowest, which is products, all the way up to the highest, which is total revenue. What they used was a unique approach where they have pre-processing with a lot of feature engineering. So they had lagged features, calendar features, rolling features. They used machine learning, and then they used ensembling. So actually combining many of the different models that they produced into and averaging them together. So this was really kind of, a unique thing that I saw here from these Kaggle competitions, is that the winning solutions were all scalable solutions, meaning they weren't producing, they weren't running through a loop, but rather they were just producing one model, and then they were using some of these different techniques like machine learning and deep learning. So the 5 key takeaways here: 1, feature engineering is really important. 2, experimentation and ensembling. Those are very important as well. Knowledge of key events, so things like holidays. I didn't really talk about this that much, but that was very important to some of the time series competitions. And then machine learning and deep learning. These are the kind of where these winning solutions are getting the results. It's not necessarily from doing like ARIMA or exponential smoothing. It's from actually applying some of these more advanced algorithms and just kind of predicting all the time series at once. Okay, so researching time series kind of led me to these conclusions. Then the next thing, what I do, so I'm an educator. I run business science. I started developing a course, and I didn't get very far with it. This was when I started developing it about 2 years ago. I had to pause several times, and we'll talk about kind of my path here. So I saw all these winning solutions, and I'm like, okay, well, how can I implement this? So I went to go, take what Sri Hari had put together in 2014 and kind of try and rework that for, an example that I could teach. And I didn't get very far. So I kind of stopped dead in my tracks because it was taking me so many lines of code just to do what he was doing for one problem. And that's not productive, right? This is why we use tools like H2O AutoML. So we don't have to do this sort of thing. But the problem is that these tools weren't built yet. So what I did was I started developing Modeltime. I kind of paused my work on the course, and I started developing this first package, which would later become an ecosystem. And really what it does is it increases our productivity. So if we remember back here, when I scroll down to the bottom here, we're looking at like 173 lines of code. This is something that would probably have taken maybe 2,000 lines of code if I was just, coding it from scratch. like the Arthur Solons of the world who have, months and months to dedicate towards these Kaggle competitions. That's not the reality in business. We need to be able to come through this much faster. So what it claims, it integrates classical models. It also uses machine learning and profit. But what it really does, it increases your productivity. It decreases the amount of code, and it improves your speed of experimenting, which is vital to be able to come up with solutions that the business needs right away. So it uses this thing called the model time workflow. We kind of stepped through it, but this is just a visual at a high level. You create a model time table, and we created ours with H2O models, 2 different H2O models. You then calibrate it, and from that calibration, you can start to visualize your forecast, test accuracy, and actually get the measure of test accuracy. And you've got your confidence intervals, and then you refit it, and then you forecast to the future. The key here is that it enables you to do this not for just one model, but it gives you a whole management system. So you can put all of your models in here, and then you can start to rank them, and you can start to then decide which ones should move forward to the next step, possibly go into production, and which ones should be left behind. And the funny thing is this may change. You may, one month it might be profit with the XG boost, but you rerun it again, and a neural net may win out, and that's okay, because you only care about making sure that you have the best possible accuracy and the best confidence. So this is what it enables us to do. Just visually be able to kind of see, how these different algorithms stack up. It also helps you from a stabilization standpoint with hyperparameter tuning and time series cross validation. We didn't discuss those. Those are kind of more advanced concepts. It's stuff that I go through in my course. We'll talk about that a little bit at the end. All right, so I just consolidated my forecast into 300 lines of code. Woohoo! But what about feature engineering? Well, same thing that happened with the modeling side. I saw up here when I started to do the pre-processing, creating the calendar features, the lag features, the rolling lags, and so on. It was taking me forever. And this was even worse. This is about twice as bad. It was taking me about 4,000 lines of code just to visualize and inspect. So I went through that same process again. I developed TimeTK. You saw that TimeTK was used for the plot time series function, the plot seasonality function. Basically, it helps us do that whole kind of pre-modeling process, from visualizing to do like the step time series signature. This stuff all comes from TimeTK. So all this pre-processing stuff in here, all of the train test splitting, all of the data visualization, that's all TimeTK. So it's a really useful package, and it actually makes time series a joy to work with. So what about ensembling? Well, we saw 6 bad models make 1 good model. Again, I developed a package for that. So you can do all sorts of different stacking with the model time ensemble. What about deep learning? So deep learning was a big winner in the web traffic forecasting and also the M4 competitions. We now have model time Gluon TS for the deep learning component. If you've never heard of Gluon TS, it's a package software that's developed by AWS. And what they do is they really focus on like these algorithms like Deep AR. It's one of the most popular. I've integrated it into Model Time, much like I did with Model Time H2O. It's just another backend. You swap out one backend for another, and it makes it super productive to make some really advanced models. And this package is also built for scale. Again, one deep learning model that you develop can forecast many, many time series. What about automation? This is where H2O AutoML comes in. So, the model time software is great, but it's nothing if you can't come through these forecasts quickly, developing models very fast. So H2O AutoML is really good on the machine learning end as a back end to model time, because it cycles through XGBoost, it cycles through great GLMs, random forest. It cycles through these models that are normally you're having to make yourself very quickly. And then the best rise to the top, and they tend to be like stacked ensembles. And they, from forecasting for many problems, when you're forecasting something like this, it works really well. So you're probably thinking at this point, Matt's been talking a lot of time about this Modeltime ecosystem. Maybe I should give it a try. And I got news for you. That's a good decision, probably the best decision you make all day. If you give Modeltime a try, I guarantee it will help you accelerate how quickly you can forecast. The ecosystem is large, so there's some pros and cons to making this decision, right? You probably saying, hey, I agree with Matt because, we're now starting to see more and more time series and we need to be able to scale it up. But, that requires change, and change requires time commitment. And do I really want to make that commitment? Well, here's the deal. I've made it super easy to get up to speed on Modeltime and the entire ecosystem. So this is the ecosystem at a high level. We're still building out a ton of software, but like at a high level, you've got machine learning, you've got ensembles, you've got back testing, you've got deep learning, you've got H2O, and then you've got time TK. So, if you try and learn this on your own, it's going to take you a while. So you're going to need to learn feature engineering, time TK, and a lot of visualization. You're going to need to learn machine learning, model time. So how to build these things. And then you're also going to need to learn ensembles. You're going to need to learn glue on TS, and also you're going to need to learn H2O. Well, I've streamlined the whole process for you. So that, months and months or years of learning, we packaged it up into a course that takes about, we'll say 2 months or so to complete. Basically what it teaches you is all like from the ground up time series analysis with a focus on building the high performance time series systems that we just talked about. You saw it here today when I forecasted with the machine learning. We got the great results with H2O. Once you learn the system, you can apply it to all these time series problems. So the only challenge is you just got to buckle down and learn it. Here's the easiest way. I'll tell you what. You get 9 hours of feature engineering. You get several challenges. You get data wrangling, transformations, 3 hours just on feature engineering. And that's just in the first part of it. The second part, you can see we're heavily focused on machine learning. So you learn some of the classical approaches like ARIMA, Profit, exponential smoothing, and T-bats. And you do still need to use those algorithms. They are, they've stood the test of time for a reason. But the machine learning component is really important as well, because we're seeing that from a scale standpoint. So you've got the boosted algorithms like Profit Boost, ARIMA Boost. You've got XGBoost and other machine learning algorithms like Mars, GLMNet, and so on. Hyperparameter tuning. So then once you get the algorithms down, you need to learn how to tune the parameters. So like XGBoost, you're going to need to learn how to do that. You're going to need to do ensembling, and then scalability with time series groups, kind of walking you through that whole process of obtaining a best-in-class model. And then also deep learning. So we've got glue on TS, this package here. And I also am working on a part 4 to it, where I'm going to add in the H2O component and also add in recursive forecasting, which is when you have like short-term lagged regressors, which is a new functionality that we've just added to Modeltime as of about 2 weeks ago. So a lot of stuff, a lot of things to learn. I do want to give you guys access to the course. I'm going to put this into the link, or this link into the chat. And if you guys want to check out that course, again, it'll be the best decision you make today, because you'll start learning Modeltime and you'll be able to help your organization out a lot. All right, so that is my presentation. I now am ready to answer any questions. I think we have, what, 5 minutes left or so?
Yes, we have 6 minutes. You can click on the Q&A tab.
Okay, all right, Q&A tab. Let me stop sharing and Q&A. Wow, we got 14 questions. I don't know if we're gonna be able to answer all of these in 6 minutes. All right.
We can go over like 2 minutes, and for the questions that are not answered, we can send an email afterwards.
Sure. Okay, so the first question I see for Richard Castro: can I use forecasting for data for trading? Um, more often than not, it's tough to forecast stocks because a lot of the times the things that are happening is not something that has happened in the past, meaning that there aren't like seasonalities to stock trading, but it ends up being that there's systemic correlations and stuff going on. So there's a lot of other approaches that I would rather use for trading, not necessarily forecasting. Vishal, is there a way to see feature engineering inherently done by the H2O in addition to the recipe created on top? I don't know if Erin's still part of this, but she may be better able to answer that one than me. So if she's still with us, she can help out. Carl S. has asked, is 1000 time series built in parallel included in the open source version of H2O? Yes, that's what I use. So at Business Science, I use H2O a ton. The AutoML, you can basically, it has the number of threads. And then, yeah, you're only building one model. So for algorithms like XGBoost and so on, they're very scalable. So for 1000 time series, it's not really any different than for 100 time series. Just one model that you produce and you forecast it. Jamil, the next question. The save model is a Mojo pipeline. No, it's not a Mojo. It's actually saving it as a R model. So H2O allows for saving the model artifacts as R objects. So we're saving it not as a Mojo, but rather just like an H2O model in R. Regarding to intermittent forecasting, do you have any special treatment? Is there a way to further tune model hyperparameters? So for intermittent forecasting, we've had really good results with just vanilla XGBoost because what ends up happening is XGBoost is really powerful at picking out like little nuances like seasonalities. And it ends up being pretty useful. I know in the M5 competition, they use the Tweety objective, which people argue that may be better for data that's has a lot of zeros. But I will say that the results that I got with XGBoost, it looked about the same when the objective was just your normal, I think just I can't remember what the normal regression objective is, but just going with that versus a Tweety, seemed to make very little difference. Okay, what was the update function doing? So this is Jessica, I didn't quite get what was being updated in the models. So what that update function was doing is actually taking our model, which has a leaderboard assigned to it. So by default, it just uses that first model of the leaderboard. But what ends up happening is we're able to update that and we're able to pick other models out beyond just the top model of the leaderboard. So I was picking the third model out, which was an XGBoost model. Tristan, did the models as specified in the demo use other covariates, multivariate modeling, or was a demo a series of 7 separate independent univariate time series models and forecasts? All right, so this kind of has a lot to unpack. So what we're doing, and I'll just show you what we're doing. So we're modeling this as a just kind of like a standard machine learning problem. So when we do the modeling, let me go back up to where the data is. So you got this recipe, all right? It's just your normal tabular data set, but has a bunch of features that have been added to it, right? So this is my target weekly sales, just like any other H2O problem. I have a bunch of date features that have been kind of broken out into different engineered or calendar features. And then I have another feature here called ID, and that ID feature specifies which time series this timestamp belongs to. So we're just modeling it as we would model any normal machine learning algorithm problem, and just kind of predicting, making an algorithm that predicts new timestamps, when I feed it new timestamps, it's going to, and a new ID and so on, it's going to produce a new value for this weekly sales. So nothing, nothing too crazy there. If you're familiar with H2O, it's, just a normal kind of multivariate, I guess you'd call it a multivariate machine learning problem. All right. Now new sodas with time series are involving transformers. Newest is the Swin transformer. So yeah, there's a lot of so time series is always evolving. The thing is that, even though they've got all these new transformers out, and they may be good, the competitions really haven't shown that any of these new transformations are being being even used. Really what we're seeing is more like business knowledge. So no adding in rolling lags of the products ends up being very important. For the M5 competition. So you have to know kind of which features to test out, and rather than using just kind of like automated transformers, you tend to have a better result if you use your business knowledge. What about these methods on the time series coming from natural data, e.g. forecast temperature? People always talk about like adding in forecast temperature, like weather patterns and those sorts of things. But the problem with those ends up being is, they're often correlated to the timestamp. So summer is normally hotter than winter, at least in Northeast. I live in Pennsylvania. So when you add in that weather temperature, it's already kind of baked into it because you have a date, and you may be using a month of the year feature. And that month tends to be warmer. So sales for, say, bicycles go up in the warmer months. So when you talk about adding in some of these other kind of features like forecast temperature, they don't necessarily always give you that much of a boost. In fact, oftentimes it's a lot better just to include the date or the calendar features from those dates. Is there a plan for a Python version in the future? We're kind of talking about that now. We are not actively working on it, but it's something that we aren't we aren't saying no to. So maybe. After the train test split, is cross-validation used for the training? So H2O AutoML automatically uses five-fold cross-validation when it comes up with the best models and in order to tune those parameters. And it ranks the best models on their cross-validations. Jessica asks, Matt, in the code examples, did you build one model for each time series or one model that could predict any of them? It's the latter. So the second one was what we did. We built one model that predicts all of the time series. George asks, you mentioned this already, but can you elaborate on what exactly happens in the refit step? Is that another training step, or is it more fine tuning? So what that is basically, in forecasting, the most important data is the data that is the closest to what you're predicting. So the end of the time series is most important. So if you're predicting the future, you want to definitely include that most recent data in there. Otherwise, your model is probably not going to forecast as good. So that refitting step, what we're doing is we're retraining the models completely. And we do have a request in for H2O to help us out with being able to just retrain one model rather than the full AutoML. But we're physically retraining that model again to take another look at the full time series, this time the full time series and not just the training set, and come up with a new model. So that's what's happening in that refitting step. How well does it perform on financial time series forecasting? I mean, that's kind of a very vague question. Every problem is different. Sometimes it'll do well. Sometimes, it won't do well. Can we circle back to the prediction interval question? I don't know what the prediction interval question was. Jessica, Matt, I was using H2O AutoML in a very similar approach, and it's been giving me really good results. That's great. I'm seeing pretty good results too. One thing I did was include information from other time series, other variables from the same product as features, but I treated it as a supervised problem in AutoML. I had to compute this lagged information and build the data set by hand. Is there an easier way to input other time series as input with model time? So what you're kind of talking about is, I think, bridges onto vector auto regression, which is where you have a bunch of time series and you try and predict them all kind of at once. Um, you can do that. I don't think it's model times really set up. We just did add a recursive function, which allows us to take your target variable and add recursive lags, meaning like lag one, lag two, lag three, and kind of run through any type of machine learning problem as kind of like an ARIMA, like how ARIMA works internally is they use those lags and they kind of fill the lags in with predictions. So we have that available now. We don't necessarily, I haven't tried it yet on using other variables from the same product. Okay.
Okay, so it's 3:05 now, and we're running out of time. I'm sorry if we did not get to everyone's questions, but we can definitely, Matt can send an email answering all the questions that weren't answered. And first of all, I would like to thank Matt for this great meetup and the workshop on H2O model time. Also, thank you to everyone who joined us today. The recording will be made available on our YouTube channel. I can share the link on the chat, and an email will be sent to everyone registered. So that's it. Matt, anything else you want to say?
Oh, yeah, just thank you for having me. I really appreciate it. Big fan of H2O, been using, your software a lot. So really, definitely, thanks for having me and really appreciate everything that you guys do for the community. If you guys have any questions, feel free to message me. You can respond to the email that you had when you log in to get the code and everything. If you have any questions, feel free to reply to that, and I'll do my best to answer you guys. All right, that's it. That's all I have.
Great. Thank you. Bye, everyone. Have a great rest of your day.
All right, bye bye.